So when we get into building high performance optimization models, we quickly find that we need more than just basic linear algebra. We need a way to express logical relationships that often appear in real world business decisions. And here we start looking at how to translate if then logic into a language a solver, Gurobi, can process efficiently. Okay, now one of the most sound ways to do this is the big M method. This is a technique for linearizing logic. And in this script, we first import the library and initialize our model. Here, import Gurobi and initialize model parts. Okay, now we define our variables. Here you can see, and we have x, which is a continuous variable ranging from to 100, and y, which is a binary variable, right? And this binary variable y acts as our switch. It is either 0 or 1. Okay, and here we define m capital. This value represents a very large number, and in this case we set it to 100 because that is the upper bound of x. A good rule of thumb is to keep this value as small as possible while still being larger than any potential value our variable can take. And here some patterns. Let's look at the first pattern. We want to say if y equals 1, then x must be at least 50. To model this, we use the expression x is greater than or equal to 50 minus capital M times 1 minus y. And think about what happens here. If y is 1, the term in the parentheses becomes 0. The whole big M term disappears and we are left with the requirement that x is at least 50. If y is 0, the constraint becomes x is greater than or equal to 50 minus 100, which is negative 50. And since our lower bound for x is 0, this constraint effectively becomes inactive. It allows x to be anything. So, okay, now we have a different logic. We want to force y to be 1 whenever x is positive. And this is expressed as x is less than or equal to capital M times y. If x is 10, y must be 1 because if y were 0, the right side would be 0, making this statement false. This is a very common way to link continuous activity to a binary decision. And that's okay. And moving on to more complex setups, sometimes we have an either or situation. And here we define three variables. Let's look at a binary switch z and two continuous variable a and b, both capped at what is 50. Okay, and we use z to decide which constraint to enforce. Okay, and if z is 1, the first constraint forces to be at least 20, and simultaneously the second constraint becomes loose because 50 times 1 makes the requirement be is at least 30 minus 50, which is negative 20. So we effectively choose which rule to follow based on that single binary bit. That's okay. And pattern 4 here. Now this is a classic application in logistics or manufacturing. We have a production variable and a binary setup variable. By saying production is less than or equal to 1000 times setup, we ensure that the model cannot produce anything unless it pays the setup cost by setting the setup variable to 1. It creates a direct dependency between the activity and the requirement for that activity to exist. Okay, that part is done. And here, while big M is classic, it can sometimes cause numerical issues if capital M is too large. And Gurobi provides a native way to handle this, which is often more stable. We set up our variables x, y, and z just like before here. And instead of doing the big M math ourselves, we use a gen const indicator here. Look at that, int 1. And we pass the binary variable y, the value true, and then the linear constraint. This tells the solver directly only enforce x is at least 50 if y is 1. Look at here. We can also do the opposite. Here we tell the solver to enforce z is less than or equal to 50 only if y is false or 0. And this is much cleaner. It avoids the large coefficients that can lead to rounding errors. We can even handle more complex requirements like a compound indicator. And this enforces that the sum of x and z must equals 100, but only when our switch is active. It makes the model far more readable and helps the solver's internal algorithms work more efficiently. And we can continue. Okay, so far we have seen how to handle binary switches, but Gurobi actually offers a suite of high-level tools for more common mathematical operations that we often need in optimization. These are specialized functions that the solver handles internally, either through clever linearization or specific algorithmic paths, which saves us the headache of manual reformulations. Okay, let me continue. Now, looking at the variable setup here, we define a list of five binary variables. Okay, sorry, here x, y, z, w, and what are they? Oh, sorry, here x, a single binary y, and then some continuous variables z and w. So notice that w is a vector of three variables with a range from negative 10 to 10. This gives us a good playground to see how these general constraints behave. Okay, and here is our first case, the max constraint. We want variable z to always equal to largest value among the first three elements of our w vector. Instead of writing out multiple inequality constraints, we use at gen const max. Okay, here you can see. This effectively tracks the peak value across those variables. And conversely, we have the mean constraint here. We create a new variable z sub mean and set it to the smallest value among those same three w variables. This is incredibly useful in risk management or capacity planning, where the weakest link or the best case dictates the outcome. That's okay. And now the absolute value is a classic nonlinear function that usually requires two separate constraints to linearize. Gurobi simplifies this with at gas abs. And this ensures that z sub abs always represents the non-negative magnitude of w u sub 0, and if w u sub 0 is negative 5, z sub abs becomes 5. Okay, and let me check here. We also have logical operators that work directly on binary variables here, and variables. And constraint means that y will be 1 if and only if x sub 0, x sub 1, and x sub 2 are all equal to 1. If even one of them is 0, y becomes 0. The OR constraint follows the same logic but only requires at least one of those inputs to be active for y sub or to become 1. And these functions allow us to build complex decisions tree within our optimization model without getting bogged down in underlying math. Okay, new part. Let me check. Okay. So sometimes, however, the relationship between variables is more complex than a simple maximum or a logical gate. A common example is a cost structure that changes at different production levels. Here we have production quantity X and a cost variable. So, instead of a single fixed price per unit, the price changes as you produce more. We define these changes using breakpoints. As you see in X points and cost points, we have a set of coordinates. You can see, 0, 0, 20, 100, 50, 200, and 100, 500. Okay, and let's think about the logic here. For the first 20 units, the cost rises to 100, which means we pay $5 per unit. Then between 20 and 50 units, the cost only goes up by another 100, so the rate drops to $3.33. Finally, for everything above 50 units, the slope steepens again to $6 per unit. To model this, we use at gene const PWL. Okay, if you missed, look at that. And this connects X and cost using two specific points, creating a function that bends at each breakpoint. To see this in action, we set our objective to minimize cost and add a requirement to produce at least 60 units. Because the cost per unit is highest in the final bracket, the solver has to balance that minimum production requirement against the increasing marginal costs. When we run the optimization, the solver looks at those slopes and finds the cheapest way to satisfy the production constraint. This allows us to model economies of scale, or in this case penalties, for our production with very high precision. Okay, and let's stop here. So far we have covered how to structure the logic of our model, but as our problems grow in scale, the way we actually construct the model in Python becomes a significant performance factor. When we move from toy examples to large-scale industry problems, we have to adapt certain patterns to ensure the model builds quickly and solves efficiently. So, first we look at variable creation. Instead of using a loop to call add var hundreds or thousands of times, we use model add vars. Okay, and this is a vectorized approach. By passing in our indices, items, and bins, this single call creates a multi-dimensional array of variables in one go. This reduces the overhead of the Python to C interface that Gurobi uses under the hood. Okay, so next let's talk about building the actual linear expressions. We use GP quick sum instead of native Python sum function. While they might look similar, QuickSum is specifically optimized for Gurobi objects. It builds the internal expression tree much faster, which becomes very noticeable when you are summing over thousands of variables. Another critical factor for solver speed is how we define our search space. Whenever possible, we provide the tightest possible lower and upper bounds on variables. This helps the solver's relaxation process. If the solver knows a variable cannot exceed a certain value, it can prune branches of the search tree much earlier, saving a massive amount of computation time. Okay, let's see how these patterns look in a real implementation, specifically for a bin packing style problem. We define 1000 items. Let me show you here much clearer. Okay. Here we use those batch creation techniques. We create a binary variable x for every item bin pair and a binary variable for each bin. Notice how we use add const. Okay, here. Now, this is a batch version of adding constraints. Inside, we use a generator expression with quick sum. This single block of code ensures that every item is assigned to exactly one bin. It is concise and more importantly, it is fast. Okay, we follow the same pattern for the capacity or open bin logic. We ensure that an item can be in a bin only if that bin is active. Finally, our objective uses quicksum to count how many bins we actually use. By building the model this way, we are giving the solver the best possible starting point. Okay, let's continue. Even with the perfect construction, you will occasionally run into models that just won't solve. This brings us to the debugging phase. If the solver returns a status of infeasible, it means your constraints are contradictory. And this is where model compute IIS becomes our best friend. Okay, let me show you clear here. Now, IIS stands for Irreducible Inconsistent Subsystem. It performs a sophisticated analysis to find the smallest set of constraints that are causing the conflict. And after computing the IIS, we loop through the constraints and print only those flagged as part of the conflict. This filters out the noise and shows you exactly which two or three rules are fighting each other. We do the same for variable bounds. Sometimes the conflict is not in a complex formula, but simply because a lower bound is higher than an upper bound. A very helpful practice is writing the IIS to a file with the .ilp extension. Okay, here. And this creates a human readable file that isolates the problem. If the model is unbounded, it means the solver can improve the objective forever. To debug this, we set the inf amp info parameter to 1. This allows us to extract the unbounded ray, which is the direction the variables are moving to reach infinity. By looking at which variables have a non-zero ray value, you can identify which constraint is missing a cap. And lastly, always rise your final model to an .lp or .mps file. Being able to read your model in a standard format is the ultimate check to ensure the math you intended is actually the math the solver received.